talking about power system stability, basically we're talking about the ability of the system to go back to a stable point after some disturbance, right? An analogy would be like forcing this ball from the bottom of the valley. If the force is small enough, it will go back to where it was. But it's if it is a hard kick, then it will go out and won't come back to a stable region, right? So what we call by stable point is usually or could usually mean two different stable points. What we call SEP or stable equilibrium point, like the bottom of the valley, a point where the system is sitting at rest and it cannot be bothered very easily. Or we could be under a UEP, which is unstable equilibrium point. So for one small second, we may be able to put this ball on the top of the hill, but with the smallest kick, it could go away, right? So this is what we mean by the SEP and UEP. We definitely don't want our systems to be working on the UEP. We want them to be working on the SEP. So by stability, we usually mean a few things. So we're talking about a steady state stability or sometimes small signal stability. We're talking about small disturbances that are happening to the system, and we want to make sure that they do not take the system away from its stable conditions. And we are always encountered with these types of small signal stabilities. And the example is like loads are always changing in the system. Generation is always changing in the system, especially renewable generations. They become more or less. So under these circumstances, small perturbations to the system should be able to withstand against all of these and be able to continue the operation. So sometimes, although it may seem that these perturbations look like they're bounded within some small regions, but if you look at the system from a longer period of time, you can see that those small perturbations may get bigger and bigger over time. One example of this is inter-area oscillations. Inter-area oscillations is related to the small disturbances or oscillations in the power that happen between two areas that are usually far away from each other, but they're interconnected using long transmission lines. So these long transmission lines usually have very big, basically, impedance. So they're called weak lines or systems that are interconnected with weak, basically, interconnections. Although there are some transactions of powers between these two areas, but with the smallest disturbance on either side, there could be some oscillations seen on the power that is being transferred from one area to the other area. And over time, these oscillations could get bigger and bigger. So these are what we call inter-area oscillations. And that's a good example of steady state stability conditions. This is an example of what I just said. If there is a transaction of power between one area versus the other area, under steady state conditions, that transaction of power is fixed. But if there's a load change and those basically oscillations are observed and decay over time, we call this system to be stable. But if there's a load change and there are some perturbations that are getting bigger and bigger over time, and that getting bigger over time may be in the matter of seconds or even minutes, that can happen. So we're talking about smaller perturbations over longer period of times when we talk about small signal stability. On the other hand, we have the transient stability or large signal stability. Under these circumstances, we're talking about perturbations that are big in nature. So like a generator goes out, the transmission line is going out because of a fault. A major load in the system is disconnected for any reason, for a fault, for example. So under these circumstances, when big changes happen to the system, depending on how stiff the system is, it could remain stable, it could remain unstable. It could remain stable as long as that disturbance is cleared within a short period of time. But if that disturbance is not cleared within a short period of time, the system may go into instability. So here we're talking about bigger signals that are happening to the system. Because of the nature of these disturbances, in small signal stability, most of the time we can take advantage of linearized models. Meaning that we're talking about short perturbations around the stable region. So we can linearize our system around that around that equilibrium point and linearize our systems. We can take advantage of linear control theory, which is a very mature branch, and do our analysis based on linear models. But for the transient stability, since we're talking about large perturbations, we usually cannot depend on linear models of the system anymore. We have to do the analysis in the nonlinear method or based on methods that have gone through research in the literature and there's still basically are being still studied. The swing equation is the start of our dynamics in power systems. The swing equation is associated with the synchronous generator. Synchronous generator has an important role in the stability of the power system because of its giant inertia. The inertia the more the inertia of the synchronous generators in the system are, the better the system can stabilize. I'm not going into the details of this swing equation. What I want you to learn is that is these two equations, 1013 and 1014. Equation 1013 is talking about a second order differential equation, which is relating the power angle of the generator with respect to the difference between the mechanical power and the electric power. So when we're talking about the synchronous generator, we're talking about the mechanical side of the system where, for example, a steam turbine, gas turbine, hydro turbine is giving mechanical power to the machine, and the machine that converts that mechanical power into electric power. So these are two different types of powers. One is coming from the mechanical sources. The other power is being given to the system, to the power system, which is an electric system, right? So when these two are in equilibrium, it means that the system is under rest. There is no changes. And we always like to keep the system under these circumstances when the P mechanical is equal to P electrical. The same amount of power that is required on the electric side is being provided from the mechanical side. If these two are equal, we would be good. We would be under good conditions. This equation 1013 is talking about that second differential equation. We can break this second order differential equation into two first order differential equations, like 1014. Where basically we have two state variables now, delta and omega. Delta was the power angle, still is there with the first derivative now. And omega is the newer state variable in here, which is the angular frequency. This is the angular frequency of the system, which is 2 pi f. So if your synchronous generator is rotating as 120 times f over p, where p is the number of poles, if the rotational speed of the machine or the rotor in RPM, revolutions per minute, is equal to 1/20 times f, which is the desired f. For example, for us, it's 60 hertz, over the number of poles of the machine. If we're able to basically maintain that speed so that this relationship is there, then we would have a fixed 60 hertz frequency on the electric side of the system. But if for any reason we're not able to rotate that rotor with that speed, then there would be a deviation in frequency of the system. And that's what we call the stability problem, basically. When in here, for any reason, you're pushing more mechanical power. So let's talk about basically a steam turbine that your system, electric system, is getting whatever megawatt, 10 megawatt as required. There is no change in the requirement of the system, but all of a sudden on the mechanical side, let's say you open the valve a little bit more to push more steam into the turbine. So PM becomes greater than PE. Because of that mismatch between PM and PE, if PM gets greater than PE, then there would be a speed up in the rotors. Because where should that extra power go to? The system doesn't want it. Mechanical system is pushing it, so it has to get accumulated somewhere. And that's the rotor of the mass of the generator, where that extra power gets accumulated in and causes that acceleration. And that acceleration will translate into the increase in the frequency of the system, right? So that would be the case where we have overfrequency. On the other side is that on the electric side, all of a sudden, all people try to, they go home, they try to turn their lights up, or and there's a summertime, weather gets hot, everybody's turning on their HVAC systems. So there's extra electric power required. And usually when that happens, the mechanical side of the system is slower than the electric side. It takes some time to be able to respond to that. So that's usually the case. Mechanical systems are slower in nature, but electric systems can be very fast. As soon as you turn the switch on, you're demanding more power. So where should that extra power come from?
Flow the generator.
Again, from the first point that you can extract that power would be the mass of the generators, which translates into slowing down. Deceleration. That deceleration means under frequency. So it's very important to keep the frequency around 60 hertz, not because we like the 16 number. That's because if you don't do that, there would be some imbalance between all of these masses, giant masses in the synchronous generators, and that could result in shutdown of the system. In these equations, there is an H coefficient also, which is kind of proportional to the inertia of the rotor of the generator. Its unit is in seconds. Roughly speaking, if H is, for example, 10 seconds, it takes 10 seconds for, giving it some context, it takes more seconds for that generator to deplete all of its energy from its mass. So in theory, if H is bigger, that is the sign that we have a more giant, basically, generator, a bigger rotor that is very hard to get kicked or we cannot. Yeah, exactly. It's harder. It's like a big guy that is really hard to push.
Wheel or something where it's like,
Yeah.
slow it down takes a lot of effort.
That's right. On the contrary, if you have a small generator, could be depleted, could be basically its speed could be impacted very easily with this mismatch between the mechanical and electric sides. Now, for stability studies, we start from a generator versus infinite bus. And what do we mean by infinite bus? Infinite bus is like a big pool of, let's do another analogy. If you have an ocean, okay? Whether or not some rivers are pouring water into it or not pouring, it doesn't bug the ocean because it's like a giant, infinite, basically, source of water. Same concept is in power systems. If you have an infinite bus is the collection of all of the generators in the system connected to a certain terminal that whether or not basically you're injecting more power into this terminal or less power, drawing more or less, it doesn't bug that terminal. It's such a stiff terminal that its voltage is always constant. Its frequency is always 60 hertz. Okay. No matter how much power you inject into it or how much power you draw from it. That's what we mean by an infinite bus. And usually in stability studies, we start from a generator, which is connected to an infinite bus. And we want to study the behavior of that generator that is connected with that infinite bus. We want to see, with the mismatch between the mechanical and electric powers, how does the power angle and frequency of that generator behave? And that's a starting point of our stability studies. For that, so we have our grid. This is a giant grid. This is our infinite bus. This is our generator, and this is the model of my generator, okay? This is the model of my generator, a source in series with XT prime. A grid, which is a combination of impedances, transmission lines, transformers, and so on. And here I have my infinite bus, which is like a source, a rigid source. In stability studies, we usually want to simplify everything into this, something like the right-hand finger. Two sources, one is associated with your generator, the other is associated with your infinite bus, and an equivalent reactance between the two. So we're ignoring all the losses. For this is usually what we do in transmission systems. We ignore the losses. We're assuming that there are two sources. One is associated with your generator. The other is associated with the infinite bus. And there is an equivalent reactance between these. Now we want to study how the stability works, how delta and omega are changing in my generator. In the models that we study, we usually take the XT prime, the direct axis reactance of the generator, which, if you recall, when we talked about the short circuit studies, we said that for transient stability studies, we usually put the XT prime value for the generator. So this is coming from there. And this E prime is the same E prime that we calculated using the XT prime, if you recall. So that's a constant. That's a constant voltage magnitude that is found when you do the power flow in this system and use XT prime here. That's the voltage that you get because of that. You call under equilibrium point, which means power flow. You find the power flow, find the voltage at this point, how much power your slack bus is giving to the grid, and then you come up with the calculations in this loop to find E prime and delta. That's what this means. And we will be seeing that in the examples coming forward. Okay, now under these circumstances, when we have two sources on the two sides and X equivalent in between, the electric power that is being delivered from the generator into the infinite bus, and this V, is considered to have a zero angle because that's the infinite bus, that's a reference point. The power that is being transferred through the system, the electric power, would be E prime E V over X equivalent sine of delta. Sine of delta. Now, what we assume to be constant in here is V, that's the infinite bus. E prime, for the purpose of transient stability studies, we also assume that E prime remains fairly constant during the short period of time that we study this phenomenon. We assume that E prime will remain almost constant. X equivalent, that's the reactance between the system and the infinite bus. Okay, that could change. We will see that later, how it can change because of the faults, because of disturbances that happen to the system. That equivalent reactance between these two sources can change. And that is one of the reasons that the system gets on or wants to become unstable. These deltas will change, right? And therefore, and delta, the power angle. The power angle, of course, under equilibrium point would be a constant number. As soon as there is a mismatch, delta starts to run away from where it was before. Now, if you go ahead and draw this, since E prime V and X equivalent under certain conditions when there is no disturbance in the system is constant, then this would be a constant term. So this would be like a sinusoid, right? It's like a sinusoid. And this is the first half cycle of that sinusoid. This is what our basically the electric side of our system must be working based on. All right, so let's assume that I'm going to keep my PM, mechanical power, to be constant. And I'm going to plot basically the electric power versus delta. So on the vertical axis, I have power, both PE and PM. On the horizontal axis, I'm going to have the delta. So what this curve shows is that based on the laws of physics, at all times, I have to be somewhere on this curve in my electric system. But my PM will remain constant. So as long as I'm keeping PM constant and there's a disturbance in the system, I always need to be somewhere on this curve on the electric side in terms of my delta. So whatever delta that I am in will determine how much power my system is receiving, the electric system is receiving, depending on what point on this curve I am. It has a certain delta and a certain PE. This is what this means, okay? The maximum power that we deliver to the system under these circumstances would be the maximum point of this E electric curve, which is equal to E prime V over X equivalent. So here we're making a few assumptions. E prime, V, and X equivalent are all basically constants. PM is constant. Under these circumstances, I have to be somewhere on this curve. Under steady state conditions, where am I at? I am at the intersection between PM and PE, which gives me 2 points. The first point is in here. The other point is in here. This is the point that I want to be in. This is the stable equilibrium point. The other point is not the stable equilibrium point. That's a UEP. Okay. Here we have an example. So this example is about finding the transient power angle curve. So basically, we're having a round rotor synchronous generator. This is my round rotor synchronous generator. This is the impedance of that generator, which is RA armature impedance, and XD prime is the direct axis reactance. I'm connected to basically infinite bus. This is the a local load modeled by its impedance, and this is basically an equivalent reactance or impedance that is connecting the terminal of my generator with the equivalent with the infinite bus. So under these circumstances, I've been given basically these impedance values. It wants me to find the excitation voltage and steady state power angle. So E prime and delta under equilibrium point. This basically comes from solving this system under steady state conditions, which is going to give me E prime to be at this point and delta 0 to be at this point. Now, the second question, which is the more important one here, is that I want to equivalent impedance between the machine and the grid. So this is based on this. So whatever we want to do in this original system is that we want to find a direct reactance between the internal source of my generator and my infinite bus. So that's the whole point of part B. We want to find the equivalent impedance between the machine and the grid. So this impedance, as you can see, is not a direct impedance. What we mean by direct impedance would be something like Z equivalent, which can be found by transforming this Y into a delta, equivalent delta, right? If we transform this Y system into a delta system, then we would be able to find that direct impedance, which is Z equivalent. So this part B is done through this conversion from Y into a delta. And in part C, we want to find the power curve angle and the maximum power that could be delivered to the grid by ignoring the resistive elements. So once you find that Z equivalent, we're going to ignore basically the resistive part. So this is going to be the equivalent power that is going to be transferred between the generator and the grid, which brings this X equivalent of this value on the denominator. E prime and VG were found in the first part of the problem. So this would be the power angle curve. PE would be 15.2809 times of sine of delta. And what is the maximum power that can be delivered? This is the maximum power that can be delivered, right? This is PE max. And now we go to the small signal. So we have two discussions in here. First is the small signal stability. The other is the transient or large signal stability. The first, which is the small signal analysis of the swing equation, is started from the original swing equation that we had. And it was here. I said these two equations are important. One is the one equation second order. The other is two first order equations, right? So let's start from this one. And instead of the P electric part, I put this equivalent, P max sine of delta. P electric was P max sine of delta, okay? And I'm going to add one term also here. This term is associated with the dampings in the generator. So this could come from different sources. So damper windings, for example, in the generators could add some damping. So in general, this damping factor does help out with the damping, with the stabilization. When there is a disturbance and we start accelerating or decelerating, this D factor, if it is positive, can result in more stability in the system and gives a more realistic, basically, view of the system. So what I did is that I used that original equation. Instead of the PE, I put it as equivalent, and I added this damping factor. I claim that this equation is a nonlinear equation in terms of delta. Why do I say that? That's because of this sine term, right? Because of this sine term, this equation is nonlinear. And I want to do small signal stability analysis. So therefore, I have to linearize this equation. What do we mean by linearization? It means that we write up delta in terms of its equilibrium point plus the disturbances. So whatever variable that is of interest to us that could have some variations, we introduce that by its equilibrium value plus some disturbances. Same thing can go, for example, with this PM. PM, which is the mechanical power, could be associated with the initial mechanical power or the mechanical power under equilibrium plus some delta PM, some disturbances or some changes in the mechanical power. Based off of that, we rewrite this equation, and then we can expand this sign, and ultimately we can write it up in this form, and it has equilibrium on both sides in bold. So this is the original, these bold portions are the original swing equation written in the equilibrium point, which means that they cancel out from the two sides. And what remains is this. This is now where this PS is a constant. So this term is, this equation is now a linear equation. The equation is a linear equation in terms of delta delta. So instead of writing up the equation in terms of the original delta, I'm writing everything in terms of delta delta, the changes around delta. And this one is a linear equation now because everything is, all of these coefficients are constant, right? This PS is constant. This is constant. Everything is constant. So this is what we mean by linearization. Okay. Also, this PS is called the synchronizing power coefficient, which we will see it's going to be an important factor in the control part of this course as well. Now, this has a general form of this linearized swing equation has a general form of this. A y double prime plus by prime plus cy equal to d, where a, b, c, and d are constants. Now, if you compare these two, 1023 to 1021, you see that your y would be delta delta, a would be this, b would be this, and so on and so forth. The solution to this equation is depending on this delta factor, which is b squared minus 4ac. If delta is smaller than 0, the solution would be this, where is minus would be equal to minus b over 2a. And the solution would be oscillatory. Sorry. Yeah. So we would have like an alpha and beta in here. This alpha beta terms are written in here. And we have a C1 and C2. These are two constants, which are coming from the initial conditions of the differential equation, C1 and C2. So when this delta is smaller than 0, the behavior would be oscillatory, which means that your delta delta starts oscillating. Most of the time in power systems, the solution that we expect is of this type, of the oscillatory term. But in general, we could have a delta greater than 0 and delta equal to 0 conditions where the solution can be found, the general solution. Now, while this table 1 is providing the general solution, but under typical circumstances, we would have the oscillatory response, which is associated with the first solution, which was associated with delta smaller than 0. Now, under these circumstances, it's customary basically to show it in terms of zeta. This is zeta, and the delta delta t could be written in terms of the zeta. So you have these two terms, cosine and sine, a constant. Look at this. Since zeta is positive, these two terms will vanish over time. When t gets greater, they get smaller. So these two terms will vanish. And finally, ultimately, your delta delta, when t goes to infinity, would be equal to delta pm over ps. Okay. And you can get a derivative of delta delta t over time to find the changes in the frequency also. So here is an example that is showing us this type of behavior. We have a round rotor synchronous generator, which is connecting to a 60 hertz grid. The machine has an inertia of 5 seconds and a damping factor of d equal to 0.138 seconds. In a steady state, it supplies 0.65 per unit of active power at a lagging power factor of this much and a voltage of that much. The generator is assumed to be lossless with a transient direct reactance of 0.25 seconds. And find the excitation voltage and the steady state power. Find a plot and so on and so forth. So it's referring you to example 10.2. Okay, so this is the problem statement. Basically here we have all the inputs. This is part of the state-to-state analysis. So we have the power, the initial electric power that we're giving to the system, power factor. And the power factor is lagging. So this gives us the complex power that we're giving to the grid. From there, we find the current of the grid. And then we can find out the internal voltage. The absolute value of the internal voltage would be E prime. and its angle would be the delta zero, the initial power angle. So our power angle curve would be based on this P max E prime times V infinite over XD prime. This XD prime is the equivalent reactance that is existing between the internal source and the infinite bus. Based on the problem statement, we are directly connected to the grid. So there's nothing between the generator and the grid. They're directly connected. Otherwise, we should have calculated what that direct impedance is. So we find the PS synchronizing power coefficient. This is zeta, this omega n. These are the terms associated with A, B, C, D in the differential equation, the delta. So we're going to plot the t from 0 to 3 seconds based on the different conditions. And we're going to basically plot the delta and omega, the delta and omega and frequency, where frequency is omega divided by 2 pi, right? So this is how the delta is changing. Remember, delta is delta 0 plus our delta delta, which is y in here. And omega is omega 0, which is 2 pi f0, plus this is your delta omega. So remember that. And we have, once you find omega, you have to divide it over 2 pi to find the frequency in hertz. So this is how your system is changing. What is important here to consider is that we want the frequency to go back to basically 60 hertz. But for the delta, we don't necessarily need to go back to the same delta. We can go from one delta to another delta. As long as basically we go from one stable delta to another stable delta, the system is stable. But for the frequency, we always need to make sure that we go back to 60 hertz in terms of operations in the system. We don't want the frequency to deviate from 60 hertz. In this problem, we basically had an initial condition change due to a sudden opening and closing of the circuit breaker. So delta delta 0, that was the initial condition change, is 2 degrees. Delta delta 0 dot was 0. But in the next problem, we have the same system, but we are changing the mechanical power by 0.2 per unit. So we're forcing some input. Remember, this equation has 4 terms, A, B, C, D. In this problem that we just solved, D was 0. So whatever change was in the system was because of the initial conditions. We're assuming a change in the mechanical power. So this is how we can simulate that. Using the previous example, if you do dPm equal to 0.2 and y0 and y0 dot equal to 0, you can get that. So dPm, instead of 0.2, we put it equal to 0. Yeah. So this was already the example 10.3, right? So the previous example was when you had this as 0. This has 2 degrees, and yeah. So this is example 10.2. This is the result of example 10.2, which should give us what we had in here. And the results of 10.3 should be when we push power, and the initial conditions would be 0. So there would be some difference between these two, as has been explained. So you get an over. So you can see that the delta goes up. Here, delta goes down. This is the difference.